Today we're going to explore one of the most profound discoveries in physics, how the chaotic dance of microscopic particles in water became the smoking gun for the existence of atoms. In the early 1800s, scientists using microscopes noticed something bizarre. When they looked at tiny particles suspended in water, pollen grains, or dust specks, these particles were constantly moving in a completely erratic, jittery manner. Picture a drop of water under a microscope. Inside you see tiny particles, and instead of sitting still, they're moving in crazy zigzag paths, constantly changing direction, never stopping. This phenomenon was first carefully documented by botanist Robert Brown in 1827, so we call it Brownian motion. Now, here's why this was such a mystery. Classical fluid mechanics said these particles should quickly stop moving. According to fluid mechanics, any motion should be damped by viscosity. The water should slow the particles down through friction until they stop. But in reality, the particles never stop moving. They jitter around forever, as long as you watch them. Scientists tried desperately to explain this. Maybe there were tiny currents in the water? Maybe convection? Maybe temperature gradients? Let me show you why all the classical explanations failed. If it were convection currents, particles would follow smooth, predictable flow patterns. But they don't. The motion is completely random and erratic. Careful experiments showed the motion had no correlation with temperature gradients or any external currents. The motion was perfectly isotropic, the same in all directions. There was no preferred direction, no pattern whatsoever. Scientists began measuring the motion statistically. They tracked how far particles moved over time. They measured something called the mean squared displacement. Take many particles, measure how far each moves in time t, square those distances, and average them. We denote this as the mean squared displacement, written as x squared in angle brackets. Now, if this were ordinary diffusion, like a drop of ink spreading in water, there's a well-known prediction. Classical diffusion says the mean squared displacement should be proportional to time. The equation is mean squared displacement equals 2 dt, where d is the diffusion constant. But here's the critical question. What determines the diffusion constant d? Classical physics had no answer for particles this small. The measurements did show that mean squared displacement was proportional to time, which was puzzling but didn't explain the mechanism. In 1905, Albert Einstein published a paper that changed everything. He asked a simple but profound question. What if water is not a smooth, continuous fluid, but is actually made of countless tiny molecules? And what if these molecules are in constant random thermal motion, jiggling around because of their thermal energy? Einstein pictured the visible particle being constantly bombarded from all sides by invisible water molecules. Each collision gives the particle a tiny kick. Let me make this quantitative. How many collisions are we talking about? Consider a particle about 1 micron in diameter. How many times per second does it get hit by water molecules? The answer is staggering. About 10 to the 21st collisions per second. That's 1 billion trillion collisions every single second. Each collision comes from a random direction and is completely uncorrelated with the previous collision. The net effect of all these random kicks is that the particle executes what mathematicians call a random walk. Einstein derived a precise mathematical relationship connecting the observable motion to molecular properties. Einstein showed that the mean squared displacement equals 2RT over 3 pi eta a na times t. Let me explain each symbol. R is the universal gas constant, 8.314 joules per mole Kelvin. T is the absolute temperature in Kelvin. Eta is the viscosity of the fluid. For water at room temperature, it's about 0.001 Pascal seconds. Little a is the radius of the particle you're tracking. And Na is Avogadro's number, the number of molecules in 1 mole of substance. Now here's what made this revolutionary. Einstein's formula makes a testable prediction. The diffusion constant d equals RT over 6 pi eta a na. This connects a macroscopic measurement to Avogadro's number. If you carefully measure the diffusion constant, and you know the temperature, viscosity, and particle size, you can calculate Avogadro's number. This is profound. You can determine the number of molecules in a mole of substance just by watching microscopic particles dance around in water. In 1908, Jean Perrin performed meticulous experiments to test Einstein's prediction. Perrin used carefully prepared latex spheres of uniform size suspended in water. Using a microscope, he painstakingly tracked the positions of individual particles over time, recording their coordinates every 30 seconds. The trajectories look like jagged, random zigzags. No pattern, completely erratic, just as Einstein predicted. Perrin measured the mean squared displacement for many particles and confirmed it was linear in time. Let's put in some numbers and see what we get. Suppose we have particles with radius 0.5 micrometers, which is half a millionth of a meter. Temperature is 300 Kelvin, which is about room temperature, 27 degrees Celsius. Water viscosity at this temperature is 0.001 Pascal seconds. Plugging into the formula, D equals 8.314 times 300, divided by 6 times 3.1415, 9 times 0.001 times 0.5, times 10 to the minus 6, times 6.022, times 10 to the 23. Working this out, D is approximately 4.4 times 10 to the minus 13 meters squared per second. This is an incredibly tiny number, which makes sense because we're talking about very small particles moving very slowly. Let's ask a practical question. How far does a typical particle move in 1 second? The mean squared displacement in 1 second is 2 dt, which is 2 times 4.4 times 10 to the minus 13 times 1 second. That gives us 8.8 times 10 to the minus 13 meters squared. Taking the square root, the typical displacement is about 0.94 micrometers, roughly the size of the particlets. So in 1 second, the particle typically moves about its own diameter. This is easily observable under a microscope. When Perrin analyzed his data using Einstein's formula, what did he get for Avogadro's number? Perrin calculated Avogadro's number as approximately 6.5 times 10 to the 23 molecules per mole. This was in remarkable agreement with other independent methods of estimating Avogadro's number, like from kinetic theory of gases. The modern accepted value is 6.022 times 10 to the 23, so Perrin's result was within about 10%. Let me explain why this was such a monumental achievement in the history of science. Before Einstein and Perrin, atoms and molecules were useful theoretical concepts, but many scientists doubted they were real. Some prominent scientists, including Ernst Mach, thought atoms were just convenient mathematical fictions, not actual physical objects. This experiment showed that you could literally see the effects of individual atomic collisions with your own eyes through a microscope. It transformed atoms from an abstract hypothesis into observable physical reality. You could count them. Let's dig deeper into the physics. Why does this random bombardment lead to diffusion? Each collision with a water molecule imparts a tiny amount of momentum to the visible particle. The momentum change delta P is roughly the mass of a water molecule times its thermal velocity. But because collisions come from all directions with equal probability, most collisions cancel out. This is the key to random walk statistics. After n random steps, the net displacement doesn't scale as n, but as the square root of n. The net displacement is proportional to the square root of the number of collisions. Since the number of collisions is proportional to time, the square of the displacement is proportional to time. That's why we see linear growth in mean squared displacement. Notice that temperature appears in Einstein's formula. What role does it play? Higher temperature means water molecules move faster on average. Faster moving molecules impart larger momentum kicks during collisions. Therefore, higher temperature leads to faster Brownian motion and larger diffusion constants. The diffusion constant is directly proportional to absolute temperature. If you double the absolute temperature from 300 Kelvin to 600 Kelvin, the diffusion constant doubles. What about particle size? How does that affect the motion? The diffusion constant is inversely proportional to the particle radius A. Smaller particles experience faster Brownian motion because they have less inertia and are more easily kicked around by molecular collisions. If you have the particle radius, the diffusion constant doubles. This is why tiny objects like viruses exhibit much faster Brownian motion than larger objects like bacteria. Einstein's analysis connected Brownian motion to the fundamental principles of statistical mechanics. Einstein's work was an early example of what we now call the fluctuation dissipation theorem. The theorem says that the friction force and the random fluctuating force are fundamentally connected. They both arise from molecular collisions. The friction force on a sphere moving through a fluid is 6 pi eta AV from Stokes' law. The same molecular collisions that create viscous friction also create the random fluctuating force that drives Brownian motion. Brownian motion and Einstein's analysis have profound applications throughout modern science. In medicine, understanding Brownian motion is crucial for designing drug delivery systems. How fast do nanoparticles diffuse through tissues? In climate science, aerosol particles in the atmosphere undergo Brownian motion, affecting cloud formation and light scattering. In nanoscience, Brownian motion limits how precisely we can manipulate tiny objects and affects self-assembly processes. Even in economics, random walk models inspired by Brownian motion are used to model stock price fluctuations. Let me pose a thought experiment. What would happen if we tried this experiment at absolute zero temperature? At absolute zero, the absolute temperature, T equals zero. Looking at Einstein's formula, as T approaches zero, the diffusion constant D also approaches zero. At absolute zero, molecules would stop moving, so there would be no molecular bombardment and no Brownian motion. The visible particle would simply freeze in place. This makes physical sense. Without thermal energy, there's no random motion. How does Brownian motion differ from classical diffusion, like a drop of ink spreading in water? In classical diffusion, we track how a concentration gradient spreads out over time. The diffusion equation is partial C, partial T, equals D times the second derivative of C with respect to x. This classical equation treats the fluid as a continuum. There's no mention of molecules. Einstein's genius was showing that this continuum equation emerges naturally from the underlying molecular chaos. The diffusion constant D in the continuum equation is exactly the same D that appears in the microscopic random walk description. Let me give you some historical context. In 1905, Einstein published 4 revolutionary papers. One paper explained the photoelectric effect, introducing the concept of light quanta. Another paper introduced special relativity, revolutionizing our understanding of space and time. A third showed that mass and energy are equivalent, giving us E equals mc squared. And the fourth paper was this one, on Brownian motion, proving atoms are real. Any one of these papers would have been enough to establish Einstein as a major physicist. He published all 4 in the same year. Here's an interesting historical footnote. Einstein won the Nobel Prize in 1921. He did not win it for special relativity or general relativity, even though those are his most famous works. He won for his work on the photoelectric effect. But many scientists argued he should have won for the Brownian motion work, because it definitively proved atoms exist. Jean Perrin won his own Nobel Prize in 1926 for experimentally verifying Einstein's predictions. Modern physics has extended these ideas far beyond Einstein's original work. There's quantum Brownian motion, where quantum effects become important for very small particles at low temperatures. There's active Brownian motion, describing self-propelled particles like bacteria that swim through fluids. There's anomalous diffusion, where the mean squared displacement doesn't grow linearly with time, but as a power law. And there's the modern field of stochastic thermodynamics, studying energy and entropy in systems dominated by thermal fluctuations. Let me leave you with a final perspective on why this discovery matters so deeply. Before Einstein, thermal fluctuations and molecular chaos were seen as just noise, something to be averaged away or ignored. Einstein showed that this noise is fundamental and carries profound information about the microscopic structure of matter. By carefully studying randomness and fluctuations, we can probe the invisible world of atoms and molecules. This philosophical insight extends throughout modern physics. Quantum mechanics, for example, is fundamentally probabilistic. Let me summarize the key points of this profound discovery. Brownian motion is the erratic, never-ending jittering of microscopic particles suspended in a fluid. Classical fluid mechanics predicted this motion should stop, but experiments showed it never does. Einstein explained the motion as the result of countless random collisions with invisible molecules. His mathematical formula connected macroscopic, measurable quantities to Avogadro's number, allowing atoms to be counted. Jean Perrin's meticulous experiments confirmed Einstein's predictions with remarkable accuracy. This definitively proved that atoms and molecules are real physical objects, not just convenient theoretical constructs. The work united the statistical mechanics of invisible molecules with directly observable macroscopic phenomena. Einstein's analysis of Brownian motion remains foundational to modern physics, chemistry, biology, and materials science.